Okay, I want to wrap up the last part of the notes that we were doing from the 5253/5.6 sections that we were working on. And the idea here is we're going to do this last example, and then we're going to kind of go through something that you may not necessarily see on the AP, but something that will kind of show you how the limit definition actually works with the Riemann sums. And then we'll wrap that up, and I'll put this video up first, give you a chance to review and revisit as needed. And then I will put up a new video for the next section, which is the fundamental theorem of calculus. All right, so in this last example that we were kind of finishing up in one class and the other hadn't even started yet, was that they're going to give you that they've already calculated the area of this shaded region right here is going to be 2. And so we want to keep that in mind, and we want to use that and the symmetry of the sine of x graph to answer questions about it. And remember that when we talk about the symmetry, we know that we have an odd function. So pretty much you can guarantee that the area of this section right here is also 2. And if I was going to calculate the definite integral, it would be a -2, because that would then be the signed area, which would be below. And we also know that this trig graph continues the same pattern over and over and over again. So at this value you're at pi, and then once we extend the graph, if we need to, up here to 2 pi, that the same max-min pattern is going to continue, and again this area is also going to be 2. So kind of just laying some groundwork for what's going to be going on with this. All right, so we take a look at the first example that they have. Now they want us to find the definite integral from pi to 2 pi. So we want signed area, which means if it's below, we want negative, above, we want positive, and that's simply this area right here, but it's below the x-axis, so the definite integral would be -2. Okay? If I want to go from 0 to 2 pi, from here to here, well, if I'm doing the definite integral, again, you have signed area, so it would be positive here, negative here. They add together, your answer would be 0. When I get to pi over 2, all right, now the first thing you want to recognize here is I'm going backwards, because it's a big number to a small number. Remember, that's the opposite of the integral from pi over 2 to pi of sine of x dx. So basically we want to take this area, which is exactly half of the shaded region, or 1, and then we want to make it the opposite because we went backwards through the integral. So the answer would be -1. In this case, I'm taking the antiderivative, or the integral, definite integral, of a constant plus the function. And what you want to remember there is that we had a nice little property that says we can take the definite integral. Whenever you have the definite integral of a sum, it's the sum of the definite integrals. So I would add them up like this. And then we're basically going to go through the problem. Now this is the definite integral for a constant, which, if you will remember, is going to be your 2, because it's kind of like the whole rectangular part of it, 2 times your b minus a. So that's going to be the evaluation for the definite integral of the constant. And then the area here, and the signed area, is going to be 2. So we end up with 2 pi plus 2. All right, now we take a look at part E. Here we're doing the definite integral of a constant times the function, which, if you will recall from our properties, we can pull the constant out. Integral of 0 to pi sine of x dx. So we pretty much just take 2 times the definite integral, which is 2 or 4. So that's going to be our first few examples here. Now we come down here and we take a look at the next one. Now the interesting thing about this next one is to realize, what really is this doing to the graph? This is taking the sine function and taking it and shifting it horizontally right 2. So kind of giving myself a sketch of my new graph. I move the graph over to the right 2, and then kind of sketch in the same sine graph that we had. And then here's that area, shaded area, that we have above. Now if I shift everything to the right 2, then this value would be 2 plus pi. Now as soon as you kind of realize that this is nothing more than a horizontal shift right 2, look at the limits on your definite integral. They want to know the definite integral from 2 to pi plus 2, which is essentially this little shaded region right here. So it actually is the same. They basically made a transformation of this integral from 0 to pi of sine of x dx is exactly the same as the integral from 2 to pi plus 2 of the sine of x minus 2. And basically this is kind of setting us up for a little bit of the chain rule working in reverse. If you think about this, if I were to look at this and I were to say let u equal x minus 2, okay? Now, thinking about these limits over here, right now we were plugging in x equal to 2 and then x equal to pi plus 2. But if I let u equal x minus 2, that means x equals u plus 2. And if x is u plus 2, you can kind of think of this as changing your variable. If I want to evaluate this as sine of u, and then, of course, you have to think about what's going to be, I got to get rid of the dx. What's the derivative of u equal to x minus 2? It ends up being du equal to dx. Okay, so I can make this change to to du, because these two things are equal. And then I can come over here and I can start changing my limits. Right now I have x is equal to 2. When x is 2, u equals x minus 2, or 2 minus 2, or 0. So my new bound on my integral by doing this substitution would be 0. When x equals pi plus 2, my u, which would be x minus 2, would be pi plus 2 minus 2, or pi. And you can kind of see that by doing a transformation, like undoing the transformation is what you're doing here. You're undoing the u substitution. You can see that you get back to this 0 to pi. And does it really matter if I say 0 to pi sine x dx, or if I say 0 to pi sine u du? It's going to be exactly the same thing. It doesn't really matter what variable you have in this location. It's still going to be an answer of 2. And so this is kind of setting us up for a preview of coming attractions, which is basically calculating definite integrals by u substitution. All right? Now, looking at this one, kind of the same idea. If I were to take in g, okay, I'm going to duplicate so I have a little bit more room here. So, and then I'll just clear out my annotation so that we have a blank sheet. So now let's come down here and let's look at this. Now, what kind of a transformation is sine of x over 2? That would be a horizontal stretch by 2. Okay? So we're basically going to take the graph that we had, which had a period of 2 pi, and now we're going to stretch it and make it twice as wide. So now it's going to come all the way out here to 2 pi for that little shaded region that we look at. So essentially it has the same height that it had before, the height of 1. All I've done is I've made it twice as wide. Now the question that you want to ask yourself might be, well, how does that affect the area of the region if I am simply doing nothing more but making it twice as wide? Kind of the interesting thing, it might be easier to think of this in terms of your rectangles and triangles. If I take a rectangle and I make it twice as wide, what happens to the area? If I take a triangle and I make the base twice as wide, what happens to the area? Hopefully you'll see that kind of the pattern that you're going to recognize is that the area is getting twice the size because you have twice the width, as long as you're preserving your height. Now I can also take a look at this in terms of the kind of u substitution. If I were going to let u equal x over 2, my du would be 1/2 dx. And now here when I start to make my substitution, I'm going to do a couple of things here. Because I'm trying to get rid of dx in this substitution, trying to change it to a simpler problem. this really is dx equals 2 du. So I'm going to kind of use this as my substitution. I'm going to take out the x over 2 and I'm going to replace it with u. I'm going to take out the dx. I'm going to replace it with 2 du. And now I also need to change my limits over here. Okay, so when my x is equal to 0, I'm using this fact over here. You can kind of solve this for x if you want. You know that x equals twice of u. Okay, or u equals x over 2. Actually, I don't need to switch it over because I'm really trying to find u. So I don't really need to solve. So we can come back in here, and when x is 0, when x is 0, u is going to equal 0. When x is 2 pi, u is going to equal pi. And so this idea is that we can algebraically justify that we think the area is going to be twice as wide by changing everything. Your x equals 0 becomes u equal to 0. Your x equal to 2 pi transforms into u equal to pi, sine of u, and then to get in and get our dx out, we're going to put in our 2 du, which is the same as 0 to pi, 2 sine u du, and what do I do with the constant? I pull it to the front, and we can verify that our area is indeed twice the area that we had before, 2 times 2, which is 4. Okay, so again, previewing coming attractions, this is called integration by substitution, because you'll notice that what I'm basically doing is substituting, 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 and substituting here. So you basically calculate this. It's kind of the reverse of the chain rule a little bit, where we're trying to get rid of the inside function that we're working out. All right, so let's take a look at h. Now, h is kind of playing on the fact that we have an odd function. If I have an odd function, whatever is above here will be below over there. They have the same area, but the signed area would be opposite. So hopefully it should be pretty straightforward that you would know that this is simply going to be 0, and then we can walk away from it. Now that's when you have an odd function. What happens when you have an even function? With an even function, you are basically going to have twice the area, because whatever is on one side is a mirror image over on the other. So that's kind of one of the other things that you're going to be working at, using the symmetry to help evaluate your definite intervals. All right, let's take a look at I here. Now I is asking us about cosine, but we have the graph that we're given is of sine. Now, one of the things that we can do here is we can turn a cosine into a sine. This is like using an identity. We can basically go 0 to pi, and cosine is the same as the sine of pi over 2 minus x. So that's your co-function identity from trig last year. And once I make that substitution, we can then go through the transformation part. I could go ahead and sketch it, but I'm going to do it the algebra way, which is I'm going to let u equal pi over 2 minus x. I'm going to calculate my du. Du would be 0 minus 1 dx. Again, notice I'm putting it in the differential form, which is kind of how you want to work when you're doing your integration. So, and also, since I'm trying to substitute for dx, I would then go dx is the opposite of du. So that's going to allow us right now to substitute u in for this pi over 2 minus x. For dx, we're going to substitute in negative du. And then I need to switch my bounds over here. So when x is equal to 0, my u is going to be equal to pi over 2 minus 0, or pi over 2. And when x equals pi, my u is going to be pi over 2 minus pi, which is negative pi over 2. So I can turn this definite interval into the definite interval going from your low bound of pi over 2 to your upper bound of negative pi over 2 of sine of u du. And then if we take a look at our picture that we had above, now remember this is going backwards, it's going big to small. So I might want to think of this as the opposite of the definite integral from negative pi over 2 to pi over 2 of sine u du. And then when I take a look at my picture, I'm going negative pi over 2, which is this area, to pi over 2, which is this area. And actually the opposite didn't matter because the odd function, they are exactly opposite of each other. So after all that work, we get that the answer is 0. And then we take a look, let's see, our last one right here. Now we've already done most of our work here. The only difference is I need to change my lower bound. Instead of x equal to pi, it's x equal to 2 pi. And when x equals 2 pi, u equals pi over 2 minus 2 pi, which is going to give me negative 3 pi over 2. So I can rewrite this. If I put all the steps in for you, we would go 0 to 2 pi sine of pi over 2 minus x, okay, which we could then convert to going to, oh, forgot my dx. If you don't have that, they take off. You don't get your credit. You got to close your integral, beginning and end, kind of like your brackets. Change my low bound is pi over 2. My upper bound is now negative 3 pi over 2. We are going to have to switch that around. Of my sine of u. Oh, you know what I didn't do? Did you see this little negative that I forgot to substitute in? That should have been a sine of u negative du, which I could pull out. And that actually makes this nicer because then I have a negative times a negative, which then makes it positive, although it didn't matter in this case because I got an answer of 0. But it will matter up here, so I'll make sure I put it in. So it's sine of u negative du. So I'm going to put the du and put the negative on the outside. And then that way, I don't even have to worry about it. I know it's large to small, but when I switch it, it just becomes the integral of negative 3 pi over 2 to pi over 2 of sine u du. So let's look at our picture. If I'm at pi over 2, let's think about where 3 pi over 2 is. This is pi. Remember, that would be 2 pi. So right here is 3 pi over 2. And again, our negative actually didn't matter again, but you do want to take it into account because I have equal areas on top and bottom. So the answer to that is also going to be 0. All right, so hopefully that is a good kind of wrap up of that last example that we were looking at, and kind of give you some ideas how to use some symmetry and properties of the trig functions especially to do some of these problems. Now, one last thing I want to do on this kind of set of sections is this idea of how would I calculate the definite integral the long way. It's kind of like when we were doing the derivative the long way. Remember when we did the derivative the long way, we did the limit as h goes to 0 of f of x plus h minus f of x all over h. And that was how we were calculating f prime of x. So that's kind of the, remember, the long way of calculating, and then we learned all the shortcut rules. So you can appreciate the shortcut rules, I am going to kind of go through how would I calculate this without doing a Riemann sum, but actually doing the limit with the Riemann sum. So we're not going to estimate it, we're going to find it exactly. So we're going to do the definite integral from 0 to 2 of x squared plus 1 dx. Okay, so we're going to kind of show you how using the limit in the long way is going to work. Your first thing that you want to do is you want to calculate your delta x, which remember is your b minus a over n, and here's your a and your b. So we go delta x is 2 minus 0 over n, and we're going to leave n in there. I want to let my n go to infinity. Remember, n is the number of rectangles that we're going to use to estimate this area. And as long as I do a finite number of rectangles, it's going to be an approximation of the definite integral. But if we let it go to infinity as a limit, then that would give us the exact area. So that's kind of the process that we're going to do. The next thing that I'm going to do is this idea of determine your subintervals. And you want to keep it general. The idea is that your first rectangle, since we're starting at 0, you want to take your width and get your next endpoint. This is kind of your right endpoint of the first rectangle, and then this would be your left endpoint of the first rectangle. Okay, and then we go, well, if I want of course, the left endpoint of this rectangle would be the right endpoint of the next one, and then we calculate the next left endpoint. And all I'm basically doing is adding my delta x each time, okay, which we're adding 2 over n. So we do 2 over n to 4, 4 over n to 6 over n, 6 over n to 8 over n, and so on and so on and so on. And we want to come up with this idea of a general rule. How am I actually calculating this? Now, when you look at this, notice that this is actually 0 over n, okay? And this is the first interval. And then my second interval, it's 2 and 4. And then my third interval, it's 4 and 6. And so the idea is, can you come up with a general rule for this? And so in my ith interval, what am I basically doing? If I am in, like here in the third interval, I really did 2 times 2 and then 2 times 3. And so if I'm in the ith interval, I would do 2 times 1 less than I, and then 2 times I to get where I'm at. And then that's going to give me that if I go to n rectangles, the nth rectangle, okay, is that we're going to end up at 2 times n minus 1 over n. And at the end, you're going to have 2 as your left endpoint, right? Because you're at the end of the interval. And so that's kind of this general sense of saying, in terms of n, how do I find out the left endpoints and the right endpoints of all these rectangles I'm adding up? Then we come down here and we're like, okay, remember we're going to pick a point to use in this subinterval, and it actually doesn't matter which one we pick, okay? For convenience, I'm going to choose to pick the right endpoint, but since I'm doing the limit as n goes to infinity, it actually would not matter which endpoint that I pick. You can pick the left, you can pick the right, you could pick the midpoint, you could also pick any random point that's in the center. It doesn't even matter. So we're just doing this for convenience. We're just going to pick mostly because I already calculated all the right endpoints and they're easy to calculate, all right? And your right endpoint is going to be, you know, I don't know my left and my right. Did y'all even notice that? Your left endpoint's on the left side, and your right endpoint is on the right side. So I am picking the endpoint that is this side each time. So I'm picking 2 over n, 4 over n, 6 over n, my 2i over n, okay? And I want to keep it general, because I'm going to be picking the left endpoint of each one. So we're going to call it 2i over n. Now remember that our formula for the summation that we're going to be doing to add up the areas, remember that we want the area of each rectangle, and the area of each rectangle is your width times your height. And remember, your width is going to come from your delta x, that's where delta x comes in. And then your height is, you take whatever endpoint you have chosen, or whatever point in the interval you have chosen, our right endpoint, you plug that into the function, and that's going to be the height that we are going to be looking at, your f of x of I star. And then your width is your delta x. And so this calculation here is the area of a rectangle, and we want to sum up the area of all n rectangles. We go ahead and we substitute what we calculated over here. In terms of our general formula, we have our 2i over n for our right endpoint selection, and we have our 2 over n, which is our delta x that we calculated. Since we know the function, we go ahead and plug and chug to the formula. Right, hold on one moment while I get my... All right, sorry about that. Coming back, so we've set up our summation, which is summing up the area of all of the n rectangles that we have. We go ahead and we plug in using the function rule, because we're trying to do this specific to the function. And then we're just going to do a little simplifying. This is nothing more than distributing the 2. This is 4i squared over n squared, multiplying and distributing this through to simplify it. And this is where the long part comes in. So now what we want to do is, this is our estimate. This is our Riemann sum. And this is only the estimate of the area, because as long as we have a finite number of rectangles, we're not going to find the exact area that we're going to look at. But if I were to take the limit of this, then I would be able to find the exact area. Now the idea is, how do I evaluate this summation? And this is kind of going back to, you probably didn't do too much with this in Algebra 2. And we're not going to focus on this, because really the only thing that you're going to see on the AP is that they might give you something that looks like this or looks more like this and ask you, what does this represent? And you have to recognize that this really is the area under the curve, or the definite integral, as soon as they add in the limit as n goes to infinity of my 2I over n squared plus 1 times 2 over n, that you should be able, this plus some given information, that recognize that this is f of x sub I star, and that this is your delta x, and that if you're taking the, oops, I need to have a summation in there. Let me add that in. I get so excited because we're doing a limit, I forget it's the limit of a sum, the limit as n goes to infinity of the sum, I equals 1 to n, that if you see this, that you know that this is calculating exactly the definite integral from, and this is where you kind of have to have some more information, 0 to 2 of your f of x, which is x squared plus 1 dx. And that there's a kind of a way to kind of come through and work backwards and choose amongst choices to recognize that that is a definite integral. But the actual, go ahead and do it the long way so that we can appreciate the shortcut that's going to be coming, is that we want to evaluate this sum. Okay, now I have put up in the folders a little summation notation review and some formulas that are going to be important kind of as you evaluate the summation. Oops, come back. All right, and what basically happens is, you're like, okay, I'm doing this summation. If you have the summation of a sum itself, you can split. So we'll split just like we do when we're doing our derivatives and our integrals and so on. And then what we recognize is that in this problem, n is actually a kind of a constant. It's our upper bound. So in a problem, the only index that we're using is I. The only variable is I. So everything else is a constant. So we pull anything that's a constant kind of out. So this becomes, we're going to pull out the 8, we're going to pull out the n cubed because they're constants in this problem. And we have the sum I, 1 to n of I squared. And then we pull out the 1 over n, again, because it has really nothing to do with this summation. We pull it to the front, it's property of our summation, and we have this 2 here. Now, there is a property that says that if I want to sum a constant like 2 from 1 to n, well, that just simply means I have how many of these 2's added up, n of them. So this ends up being, this part evaluates to this, okay? There is a special summation formula. There's one for a constant I squared, and I cubed, which is why we break these up. So the summation formula that you would memorize if you were in BC Calc, but we're in AB, so we're not going to worry about it. We're just demonstrating here that this summation gets replaced with this little closed formula, and that's what it's equal to. And then we do a little simplifying. We get ourselves to, oh, a nice little rational function, because we know how to take the limit of the rational function. So this right here is what we call summation evaluation, which is rewriting the sum so that it is not this big long bunch of things added up together. It's kind of like the shortcut formula for your summation. This is called the closed formula for the summation, where I am only dependent on n and not dependent on the I. I don't have to have all these terms that are being added up together. And so this is usually considered a better form and setting us up to take the limit. So we want to calculate our definite integral. We're going to take the limit, and the sum, since it evaluated to this, means I'm going to take the limit of a nice rational function. And if you remember, when we do rational functions, you only have to worry about the leading coefficient and the leading coefficient here, they have the same degree. They cancel out. Our limit is going to be 14/3. So that tells us that the accumulated area on this function from 0 to 2 is going to be 14/3. So if I were looking at a picture, here's my x squared plus 1. So if I want to know what this area represents from 0 to 2, that area is actually exactly 14/3. And that is the long way. Just like the limit definition for derivatives, the limit definition of an integral, there is a long way to calculate them. But we're going to do the short way, and that's coming in the next section. Okay, so I'm going to stop there for this lesson, and we'll pick up with the fundamental theorem of calculus.